Hey guys, welcome to the last video in the Chapter 17 Kinetics lecture series. In this video, I'm going to work an example of a reaction mechanism problem where the slow step is not first. The initial step is fast, the slow comes later. So here's our problem. We've got our three elementary steps, fast, slow, and then fast. What we're going to do is we're going to predict the overall reaction. So that's finding intermediates, catalysts, getting rid of them, and then predicting the overall rate law. If you want to give this a shot and then pause the video, I'll catch up to you. All right, so first thing I'm going to do is predict the overall reaction. So I want to get rid of intermediates first. So intermediates, again, are something that are produced and then consumed. What else do we have? We have produced and then consumed. Nothing else produced. Water is not consumed. All right, that's it. So those are our two intermediates. So these will not be in the overall reaction order. We also cannot find them in the rate law as well. All right, so oops, white is not going to be helpful. Let's write the overall reaction. So what we have left on the reactant side is 2NO plus hydrogen plus hydrogen. So that's here, 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 to produce nothing from the first step, water, nitrogen, and water. So cleaning up this overall reaction a little bit, so we've got H2 here, we've got two of them, so I can reduce that down to 2H2. And then same thing with the waters here, there's two of them. I need to erase something. But we got 2H2O, and then I accidentally erased this. So that's the overall reaction. Check, we did that. Now we have to predict the rate law. So the rate determining step here is the second step. It's the slow step. There is a constant associated with that step, and I'm going to call it 2. If I were to say 1, 2, 3 on the elementary steps, that's why I gave it a 2. So I'm going to click forward here. Actually, let me just erase this. So if the rate is determined by the slow step, what we have right now for rate law is rate equals K2 concentration of our reactants. So concentration of H2 times concentration of N2O2. But there's a problem. That N2O2 is an intermediate, so it cannot be included in the overall rate law. So I have to go to the reaction before it to find out where it came from. And then also that's going to give me a way to replace it as a variable. So I'm actually going to write this equation on the next slide so that we can work with a little bit of room. So the equation that we're going back to is this one. So 2NO, this is fast and ends up in equilibrium. Makes N2O2. So remember, there is a constant associated with each of these reactions. So the forward reaction is K1. The reverse reaction is the inverse of K1. It's in equilibrium, so the rate of the forward equals the rate of the reverse. So I can set these two equal to one another. And so for this side, we're going to see that K1 is concentration of NO squared. And K to the negative 1 is concentration of N2O2. Where did I get O squared? So another way to write this would be NO plus NO. And then we would have two of these, which is the same thing as NO squared. So just kind of an explanation of why that's a squared value. All right, so we've got our two rings that are equal to one another. The whole purpose of this exercise is to get this into O2 by itself, because I want to replace that variable on the other slide. So to get into O2 by itself, I'm going to divide by the K inverse. Those cancel, we're left with N2. So here is the variable I want to replace, and here's what I'm replacing it with. So here's the variable I want to replace. Here's what I'm replacing it with. So now we're going to go do that on the previous slide. So I want to replace this guy right here. So I'm just going to simply rewrite what stays. And then I'm going to change colors just so you see that I replaced it. And I'm replacing it with this right here, right? It equals to that. So replacing it with K1, K -1, and O squared. So now we have a rate law that does not contain intermediates. And now we know this is in fact the rate law for this reaction. So if I were to just to clean up this mess, I would have rate equals, and you could do K asterisk, or you could just write it H N O squared, and then a little legend over to the side that says, hey, by the way, Miss Maz, K asterisk means this and this combined. So I just combined this and this to make that. So that's how we determine the rate law of the overall reaction when the first step is a fast step. Initial step is fast, a little bit more work that goes into it. The other thing you notice about this problem is there are 3 reactions. We weren't really bothered with the third one. And that's because it doesn't really matter when it comes to the rate. Like, we're going to get bogged down in step 2, but once we clear step 2, everything is going to happen super fast, and it's not going to affect the rate at all. So that's why we didn't address the third equation, because it didn't matter. It's not going to limit this reaction. That's the end of kinetics information. I hope you guys found this helpful.